Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as rotational motion. Let's see this. Let's study theorem of parallel axis. Let's see theorem of parallel axis. First, let's derive the theorem before we write the theorem down. So let's consider a rigid body. Right? Let's consider point O. Point P. O is the axis of rotation. O is the axis of rotation. You want to find out the moment of inertia of point P. Right? Let's also drop a perpendicular from here. Let's consider this point as C, which is at a distance of R, and this is D. Now, what do these points represent? Let's write them down. So you will say, consider a rigid body. Consider a rigid body of mass m rotating about an axis passing through point O. And perpendicular to the plane. So mass of the body we have defined and O is my axis of rotation, right? Now let's assume that C is the center of the mass of the body. C is center of mass. C is the center of mass of the body at a distance of R from the axis of rotation. At a distance of R from the axis of rotation. Right? In which case, let's assume that IO is the moment of inertia of the body about an axis passing through point O. IO is moment of inertia of a body about an axis passing through point O. Right? Let's also consider that IC is the moment of inertia about a parallel axis passing through C. Moment of inertia about a parallel axis passing through C. Right? Now, let's try to find out what is the relationship between IO and IC. Now, let's consider a small element of mass dm situated at point P on the body. Consider a small element of mass dm situated at point P. Right? Let's assume situated at point P. Join PO and PC. Join PO and PC and draw PD perpendicular to OC. Draw PD perpendicular to OC. Right? Now, by definition, what is moment of inertia? By definition, moment of inertia is nothing but the product of mass and square of the distance. Therefore, I can say moment of inertia of element dm passing through O. Moment of inertia of element dm passing through O right? The distance between them and the mass will be nothing but the mass, that is dm, into distance, that is op square. That will be the moment of inertia of point P about an axis passing through O. Now, in that case, what will be the moment of inertia of, this is moment of inertia of a point. Therefore, what will be the moment of inertia of the entire body? Moment of inertia of the entire body will be nothing but the integral of the moment of inertia of a given point. Therefore, I can say that moment of inertia of a body passing through O will be integral of OP square into dm, right? Similarly, I can find out moment of inertia of element dm passing through, moment of inertia of element dm passing through C will be nothing but dm into the square of the distance. The distance is nothing but pc. So dm into pc square. Therefore, I can say moment of inertia of body passing through C will be nothing but integral of pc square into dm. Okay. Now, let's leave this and let's get to geometry. Now, I can say that OP square is nothing but PD square plus OD square, right? I can say that in triangle OPD, OP square is nothing but PD square plus OD square, right? Now, this can be written as PD square can be written as PC square minus CD square. Before that, I can say that PD square, let's leave it as it is. OD square can be written as OC plus CD the whole square. Right? Now, this can be written as PD square. This is in the form A plus B the whole square. A plus B the whole square is A square plus 2AB plus B square. Right? Now, I can say but PD square is nothing but PC square minus CD square. Therefore, I'll get that OP square is PC square minus CD square plus OC square plus twice OCCD plus CD square minus CD square plus CD square gets cancelled. So I'll get OP square is nothing but PC square plus OC square plus twice OCCD, right? Now, I can say that but moment of inertia of the body about O is integral of nothing but OP square into dm. OP square you just found out. So IO is integral of PC square plus OC square plus twice OCCD into dm, right? So this is going to be nothing but integral of PC square into dm plus integral of OC square into dm plus twice integral of OC into CD into dm, right? Now OC we have said is R. OC is the distance between the axis of rotation and the center of mass, which will not change, but OC is R, which is a constant, right? In that case, I will get IO is integral of PC square with respect to m plus R squared with respect to m plus 2R CD with respect to m. I have substituted the value of OC as R, right? Now, I can therefore say integral of dm. integral of the element of mass is nothing but the total mass of the body. Therefore, I can say that now integral of PC square into dm, we had already said that integral of PC square into dm is nothing but IC, that's the moment of inertia about point C, plus r square. Integral of dm is nothing but m r, we already did an r square, plus 2r integral of CD into dm, integral of CD into dm. Now I can say that let's assume that the center of the mass coincides with the origin. Let center of mass coincide with origin. Let's assume that the center of mass coincides with the origin with the line CD on x-axis. Right, in which case I can say that CD will be the x coordinate of dm. If it's on x-axis, CD will be the x coordinate of dm, right? And therefore I can say by definition of center of mass, I can say that integral of CD with respect to m is nothing but integral of x with respect to m, which is nothing but integral of dm is m, and this is cm xcm, right, which I said is going to coincide with the x coordinate. CD will be the x coordinate of dm. Now as the center of mass coincides with the origin, center of mass coincides with the origin, the distance between C and M will be 0, that means xcm will be 0. Therefore integral of CD into dm will be nothing but integral of x into dm, which will be equal to 0. So if I substitute this in my original equation, I will therefore get IO is equal to IC plus MR square, and that's my theorem of parallel axis. So what is the theorem of parallel axis state? Right? How do I define theorem of parallel axis? It says that moment of inertia of a body about any axis, moment of inertia of a body about any axis is equal to the sum of moment of inertia of the body, or sum of moment of inertia about a parallel axis, moment of inertia about a parallel axis passing through the center of mass passing through center of mass, and the product of mass of the body and the product of mass of the body and the square of the distance between the two axes. Square of the distance between the two axes. Right? That's my theorem of parallel axis. Right? Next, let's see theorem of perpendicular axis. right? Now, first let's derive the theorem and then we'll write the theorem down, right? Let's consider a rigid body. Let's consider two axes on the body. This is my y-axis and x-axis. X-axis and y-axis are on the body, and z-axis is perpendicular to the body. This is z-axis which is perpendicular to the plane of the body, right? Let's consider point P on the body whose mass is dm. Draw perpendicular on x-axis and y-axis. This is perpendicular here, this is perpendicular here, and join this, right? So in that case, this will be y, this is the distance of the given point, this is the distance of origin from the y-axis, and this distance is going to be x. Let's call this point as say n, and let's call this point as say m, right? Let's write the theory down. Let small element of mass dm, let small element of mass dm be situated at point P x, y, right, on the lamina. In which case I can say that join OP and draw PM and PN perpendicular, PM and PN perpendicular to x and y axis, right? So in that case I can say that the element dm, is at a distance of y from the x-axis. This is its distance from the x-axis. It is at a distance of y from x-axis, and it is at a distance of okay. Therefore, I can say that moment of inertia of the element about x-axis, moment of inertia of the element about x-axis is going to be nothing but mass of the body into square of the distance, so it will be nothing but dm into y square. Therefore, I can say that moment of inertia of the lamina about x-axis is going to be integral of y square with respect to m. Similarly, I can say that moment of inertia of the element, or before that I can say that the element dm is at a distance of x from y-axis. Therefore, I can say that moment of inertia of the element about y-axis is going to be integral of x squared dm, right? Therefore, I can say that x squared dm. Therefore, I can say that moment of inertia of the lamina about y-axis is going to be integral of x square dm. Now once I have this, then I can say that also the element dm is at a distance of say is at a distance of OP from z axis. Say also the element dm is at a distance of OP from z axis. Is at a distance of OP from z axis. Now if it is at a distance of OP from z axis, then I can say that moment of inertia of the element about z axis, moment of inertia of the element about z axis is going to be nothing but OP square into dm. Therefore, moment of inertia of the lamina about z axis will be integral of OP square into dm, right? Once I have this, then I can say that by Pythagoras theorem I can say OP square is nothing but ON square plus PN square. OP square is nothing but ON square plus PN square, right? ON is nothing but y square. PN is nothing but OM square, so that will be nothing but x square. Therefore, I can say OP square is nothing but y square plus x square. Okay. Now, therefore, I can say moment of inertia about z axis z axis is nothing but integral of OP square into dm, integral of y square plus x square with respect to m, which is nothing but integral of y square with respect to m plus integral of x square with respect to m. Integral of y square with respect to m is nothing but Iy, moment of inertia about y axis, and this is moment of inertia about x axis. Thus, I get Iz is equal to Ix plus Iy, right? That's my theorem of perpendicular axis. So how do I define theorem of perpendicular axis? I can say that moment of inertia of a plane lamina, moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to the sum of the moment of inertia about two mutually perpendicular axes in the plane of the lamina, mutually perpendicular axes in the plane of lamina and intersecting at a point where the perpendicular axis cuts the lamina. So that is Iz is equal to Ix plus Iy. Now that we know what is moment of inertia, let's try to find out moment of inertia of different bodies. First, let's try to find out moment of inertia of a thin uniform rod. Now, if I'm finding out the moment of inertia about thin uniform rod, first let me find out the moment of inertia about an axis passing through the center of the rod and perpendicular to the rod. About an axis passing through the center of the rod and perpendicular to the rod. Right? Now, let's first consider a thin uniform rod. This is my thin uniform rod. Right? Moment of inertia is passing through the center. So this is my moment of inertia passing through the center and is perpendicular. So C is the center. If L is the total length of the rod, that means this will be L by 2 and this point will be minus L by 2. Let us consider a small element of the rod. Let us consider a small element of the rod at a distance of R from the center. Let this element be dr. Okay. So, let's see how do we do this. I can say that consider a uniform rod. Consider a thin uniform rod of length L and mass M, right? Rotating about an axis passing through the center. Rotating about an axis passing through the center and perpendicular to the rod. Right? Okay. Now let's assume that let rho be the mass per unit length. Let rho be the mass per unit length. If rho is the mass per unit length, that means the total mass is mass per unit length into the length. Now, I can say that the rod can be divided into a number of small elements. The rod can be considered to be divided into a number of small elements. Number of small elements. Right? Now let us assume that let dr be the length of an element situated at a distance of r. Let dr be the length. Let dr be the length of an element situated at a distance of r, right, from the axis of rotation. Right? In which case I can therefore say what will be the mass of element dm. Mass of element dm will be mass per unit length into the length. Length I said is dr, so it will be nothing but rho dr. Now moment of inertia of this element about given axis of rotation. Moment of inertia of this element about axis of rotation. By definition, moment of inertia is nothing but mass into square of distance. Mass we found out is nothing but sigma dr. Distance I said is r square. Right? Therefore, I can say what will be the moment of inertia of the rod. Moment of inertia of the rod moment of inertia of the rod will be given by I, which will be nothing but integral of the moment of inertia of the small element. So that will be nothing but rho r square dr. Now the rod is on both the sides, so I'll have to take the limit from minus L by 2 to L by 2. The axis of rotation is passing through the center. That means if the total length is L, each side on either side of the axis of rotation will be L by 2, right? So this is going to be sigma comes out minus L by 2 to L by 2 r square dr. Integral of r square is nothing but r cube by 3. So sigma r cube by 3 when the limits are between minus L by 2 to L by 2, right? How do I solve this? This is rho by 3, upper limit minus lower limit. So this is going to be L by 2 the whole cube minus L by 2 the whole cube. Upper limit minus lower limit. So this is going to be rho by 3 L cube by 8 minus L cube by 8, right? So this is going to be nothing but rho by 3, this is L cube plus L cube, 2L cube by 8, right? So this is going to be sigma L cube by 12, right? Now this can be written as, sorry, not sigma, rho L cube by 12. Now this can be written as rho L into L square by 12, but rho L is nothing but the mass of the body, so ml square by 12. So moment of inertia of a body about an axis passing through the center and perpendicular to the rod is nothing but ml square by 12. Alright. Now, how do I find out the radius of gyration of this rod? Right. Now, I can say that if K is the radius of gyration of the rod, radius of gyration of rod about the axis of rotation, then I can say that I is equal to mk square, in which case I can say that k is equal to square root of I upon m. K is equal to square root of I we just found out is nothing but ml square by 12, ml square by 12 by m and m gets cancelled, so k is equal to square root of L square by 12. 4 3s are 12, so I could have written this as 2 root 3. 1 upon 2 L square by 12, so this can be written as L by 2 root 3. That will be the radius of gyration. Now, let's try to find out the moment of inertia of the rod about an axis passing through one end and perpendicular to the rod. So far we were rotating the rod about an axis passing through the center. What if I want to rotate the rod through one end of the rod? For example, I'll show you this. Now let's find out moment of inertia of the rod about an axis passing through one end, passing through one end and perpendicular to the length. This is my rod. I want to find out the moment of inertia about point O, which is passing through one end and perpendicular to the rod. I already know the moment of inertia about an axis passing through the center and perpendicular to the rod. We also know that the distance between point O and point C is L by 2 because C is the center of the rod, right? In that case, I can say that consider a thin uniform rod of mass m and length L. Consider a thin uniform rod of mass m and length L, right, with axis of rotation passing through 1 and O, with axis of rotation passing through 1 and O. Let C be the center of the mass of the rod. Let C be center of mass of rod. Right? Now, let's assume that IO is the moment of inertia of the rod about an axis passing through 1 and O. IO is moment of inertia about axis passing through O. And let's assume that IC is the moment of inertia about an axis passing through the center of mass. IC is moment of inertia about axis passing through center of mass, right? In which case I can say that IO is equal to IC plus MR square. This is by theorem of parallel axis, as IO and IC are perpendicular to each other, and also I can say that IC is nothing but ml square by 12. Therefore, I can say IO is equal to ml square by 12 plus mr square. But what is R here? R we said is L by 2. So in that case, I can say IO is equal to ml square by 12 plus m L by 2 the whole square. So this is ml square by 12 plus ml square by 4. Right? 12 is the common denominator. So this is ml square plus 3 ml square by 12. 4 ml square by 12, which will give you ml square by 3. Right? Ml square by 3. Now, let's assume that K is the radius of gyration. Let KO be radius of gyration, in which case I can say KO is square root of I by M, IO by M, which is nothing but square root of IO, that is nothing but ml square by 3 by M. So in that case, this is going to be square root of L square by 3. So KO is going to be nothing but square root of L square by 3, that is L by root 3. That will be the radius of gyration. Okay, we will stop this here for the day. Thank you very much.